Our goal with these videos is to create the most accessible path towards understanding vertex algebras as possible. So this is a notoriously difficult subject to study, but I really think that it is possible to make this accessible to more people than study it right now, and that's the big goal here. So in previous videos, we've looked at the general idea for a vertex algebra as kind of a generalization of a commutative associative algebra and a Li algebra. And we've kind of looked at the definition, but not super carefully. And in this video, well, we're not going to quite look at the definition, but the main goal is to get a handle on the types of vector spaces that you should be thinking about when we start looking at vertex algebras. So let's just go ahead and recall the standard idea behind the whole thing in the first place. So a vertex algebra is a vector space V over a field, usually that field is the complex numbers, that is endowed with infinitely many products. And so this negative first product, so we can think about this as the negative first way of multiplying u and v, but instead of putting a multiplication symbol or something like that, we just put it as a subscript of the u, but you want to think about that as the negative first product. And so this is like as close to being a commutative associative algebra product as you can get in this world of vertex algebras. And then the zeroth multiplication, u0v, that's as close to being a Li algebra bracket as you can get within a vertex algebra. And then going up this direction to the non-negative products, you have further generalizations of the Li bracket. And then going down in this direction, you have further generalizations of the commutative associative product. Now let's zero in on this part. So a vertex algebra is a vector space. So there's a bunch of types of vector spaces. What types will be important to understand to really understand the definition of a vertex algebra and the examples of vertex algebras? Well, that's our big goal for today. Unfortunately, many of the examples of the vector spaces underlying common associative algebras and common Li algebras are not suitable for forming a vertex algebra. And it's really summed up by this sentence right here. The common examples of associative algebras and Li algebras are often representable as matrices. And so you could have n by n matrices with entries in some field. So that's an associative algebra where you have the matrix product. Or you could have a Li algebra, and many Li algebras are representable by matrices, just like SL2, which we looked at in a previous video. So that's the space of all trace zero matrices that are 2 by 2. So in other words, we have entries A, B, C, D, where A plus D equals 0. And then the Li bracket here is just given by the commutator. So if we were to do X bracket Y, we would have something like XY minus YX. And like I just said, this is not a good model to come to grips with the definition of a vertex algebra. We'll need to think about different types of vector spaces. And so what types? Well, let's get into that now. So if algebras constructed from matrices are not a good model for bridging the gap to vertex algebras, what would be a good model? Well, luckily we've got a fairly simple one, and that's the lowly polynomial ring. So let's consider C adjoint X, and so this is going to be all polynomials with coefficients in the complex numbers. So we could write this as A0 plus A1X all the way up to AN X to the N. And here we have AI, our complex numbers, and n is bigger than or equal to 0. So even though this is something fairly simple that you probably study in like an abstract algebra 1 class when you do the polynomials section, this is actually a good starting point for understanding vertex algebras because you can often find some polynomial type structure within a vertex algebra. So one thing that I want to notice about this that makes it very different than the examples involving matrices is that this is infinite dimensional. So let's maybe go ahead and write that down. And, well, how can we see that it's infinite dimensional? Well, we can actually write down a basis for this thing, and the basis has infinitely many elements. So we have the constant term 1, that's an element of the basis. We could have x, x squared, and so on and so forth. So notice there are going to be infinitely many terms in this basis, and so that means this thing is infinite dimensional. And another thing that we can see is that this thing is partitionable into parts that have a certain degree. And so notice that we could look at all of the degree 0 parts, but that'll just be all of the numbers themselves. And then we could look at all of the degree 1 parts, and that's just going to be all of the linear polynomials. In other words, this is just going to be c times x. So what I mean by that is this is just everything of the form ax, where a is some complex number. Great. And then you can see that we can generalize this very easily. Notice we could have degree n would be cxn, and here this is just going to be ax to the n, where a is some complex number. And I want to notice that this polynomial ring, c adjoin x, will actually break down into a direct sum of these vector subspaces. So notice this is going to be the direct sum, n goes from 0 to infinity, of cxn. And we've got this nice rule as well, that if you take something of degree n and something of degree m and you multiply them, you get something of degree n plus m. So that's an important structure as well. Okay, so this is a nice like toy example, but it actually doesn't get us very far. We'll need to generalize this a little bit more before we can actually get something that looks closer to a vertex algebra. And so let's do that. So we just got done talking about polynomial rings, and we latched on to two things that were true about a polynomial ring that make it a nice model to get our brains thinking in the right direction of a vertex algebra. First, it was infinite dimensional. And second, it was partitionable into pieces that were kind of simple. And in this case, we partitioned it into pieces where everything had the same degree. So constant terms had degree 0, and then linear terms, so something like a times x were degree 1, and then so on and so forth. Now we want to jump into a next example, which is really just a generalization of that first polynomial example. Now we'll have polynomials with infinitely many variables. And I'm going to put our infinitely many variables to have a name that is maybe consistent with some structure that we could give them later involving vertex algebra ideas. So here, I'll say the variables are x sub minus 1, x sub minus 2, x sub minus 3, and so on and so forth. Okay, so since this thing has infinitely many variables, it's clearly infinite dimensional. So the next thing we want to notice is, can we break this apart into simpler pieces? And we can if we think about these indices as being some sort of way of weighing these elements. So let's say we've got a monomial from this space, so we can write that monomial in the following form: x sub minus m1 all the way up to x sub minus mk. And here k could be bigger than or equal to 0. So if k is equal to 0, that's like an empty product, so you just get a constant, or the constant 1 in this case. So what we want to do is somehow define something called the weight of this monomial. And the natural way to define the weight of this monomial will be just the sum of all of these indices. So here we have m1 plus all the way up to mk, but we're going to change the sign really to fit in line with some stuff that we do later. So now let's look at a couple of these weight spaces. So notice if we have the weight 0 space, so that's just going to be the span of the constant polynomial 1. So that's the only thing that has weight 0. Now let's look at the weight 1 space. So this space is also kind of boring, so this is going to be the span of x sub minus 1. Now let's look at the weight 2 space. So now it's getting to be a little bit more interesting. This is going to be two-dimensional. We have x sub minus 2 and then x sub minus 1 times x sub minus 1. Great. And then next, maybe we could write down the weight 3 space. So again, this is going to be more interesting. This is going to be x sub minus 3, x sub minus 2, x sub minus 1, and then x sub minus 1 cubed. So notice each of those have weight 3. And now you can kind of see where we're going. There's going to be some sort of one-to-one relationship between partitions of the number n and the weight n basis. So as we'll see in the next video, we can give this algebra the structure of a vertex algebra, but that's not what we're going to do here. The whole point of what we're doing here is just getting used to the type of vector spaces that turn into vertex algebras. And this is a really good example. So polynomial ring in infinitely many variables, that's a really good way to start thinking about these vertex algebras. Now, the next step would to think about be a polynomial ring in infinitely many variables where those variables do not commute. So let's go ahead and look at one of those. On the last board, we discussed how polynomial rings in infinitely many commuting variables were an important model to start thinking about vertex algebras. We didn't strongly point out that those variables were commuting, but by using the word polynomial ring, you generally think that those variables commute. So now what we want to do is start thinking about a similar structure, so polynomial rings, but now the variables do not commute. So that's going to be also an important model to start thinking about vertex algebras. And you might say, well, what's the simplest way that we can do that? Because you should always try to think about the simplest way of doing it first, understand that, and then move on. And the simplest way is to have them almost commute. So maybe instead of when you switch them, you get the same thing. When you switch them, you get the negative. So they anti-commute. And so there's a name for that, and that's called like the exterior algebra or something. So we'll call it like this, big wedge, and then we'll call the variables phi sub minus 1, phi sub minus 2, phi sub minus 3, and so on and so forth. So you want to think about this exactly the same as the last example, except now the variables do not commute, and in fact they anti-commute. And by anti-commute, I mean that if we take phi sub minus m, phi sub minus n, and we switch them, we get a minus sign. So we get something like that. Good. But now notice if we switch those and get a minus sign, that means if you multiply one variable by itself, so like phi sub minus m, you are going to necessarily get 0. Because if you were to commute it, you would get negative itself, but then you'd have something equal to the negative of itself, but the only thing that has that property is 0. So now we can similarly put the same sort of idea of a weight to monomials here as well. And so let's maybe go ahead and do that. So notice that the weight equals 0 subspace here will just be, again, the span of the number 1. So it's just like the constant polynomial terms. And then the weight 1 space is going to be the span of phi sub minus 1. And then the big difference happens here at the weight 2 space. This is going to be the span of phi sub minus 2. You're not allowed to have phi sub minus 1, phi sub minus 1 because of this anti-commutativity up here that gives us 0 whenever you take the product of something with itself. Okay, so next maybe we could look at the weight 3 space, and notice that's going to be spanned by 2 vectors now, phi sub minus 3 and phi sub minus 2 times phi sub minus 1, and then you could just keep going. So I want to notice here that the basis for the weight n space, it's not quite all of the partitions of n, but it's something to do with all of the partitions of n where their parts are distinct. So you're never allowed to repeat anything. And in fact, you can show that this entire space up here is spanned by the following monomials. Phi sub minus m1 all the way up to phi sub minus mk. And here we're going to have this rule that m1 is strictly bigger than m2, is strictly bigger all the way down to mk, which is strictly bigger than 1. So notice that strict inequality does not allow for any repetition here. Now compare this to the spanning set for our original example of infinitely many commuting variables, and there we allowed for equalities. So we just looked at examples of polynomial rings with infinitely many variables, one where those variables commuted with each other, and one where those variables anti-commuted with each other. And both of those are going to serve as excellent steps towards understanding the notion of a vertex algebra, like in a larger sense. So maybe before we finish this video, I want to look at one more example, and this is going to be something like a polynomial ring with infinitely many variables, but now the variables don't commute in a more interesting way. So let's go ahead and do that. So Lie algebras give rise to many important examples of vertex algebras. And in fact, many vertex algebras can linearly be thought of as polynomial rings with infinitely many variables, but those variables come from Lie algebras. And the commutativity of those variables come from the structure of the bracket on the Lie algebra. And that's one of the examples that we want to end with. And so we want to first look at this thing called the Verasoro Li Algebra. So it itself is very interesting. And this is an infinite dimensional Lie algebra. Maybe we'll call it V. And it is spanned by two types of objects. So first of all, it's spanned by these things which I'll call L sub m, as m runs over all of the integers. And then it also has this thing called C, which is often called the central element. And, well, if we've got those things that are building this Lie algebra, well, we need to talk about how to take their bracket, in other words, their Lie product. And it's going to be defined as follows. So L sub m, L sub n will be equal to m minus n, L sub m plus n, plus m cubed minus m over 12 delta m plus n comma 0, and then this central element C. And notice I've been calling that C a central element, and that's because it commutes with everything. So let's maybe write that like this: Lm with C is equal to 0, and that's going to be for all m. So let's maybe do a couple of examples real quick. So maybe first of all, we'll do L sub minus 2 bracket L sub minus 3. So notice that will give us minus 2 plus 3, because it's going to be minus 2 minus minus 3. And then L sub minus 5. But that's it, because since minus 2 plus minus 3 is not equal to 0, that Kronecker delta will give us a 0. So notice here we just have L sub minus 5. So somehow we're combining this thing with a minus 2 index and a minus 3 index and getting something with a minus 5 index. So that's actually important to notice. Okay, then maybe we'll do another example. So let's maybe do L sub 2 with L sub minus 2, like that. So notice here, we're going to get 2 minus minus 2, L sub 0. So that's going to be 4 times L sub 0, but now 2 plus minus 2 is equal to 0. So that means we'll get this term as well. So we'll have m cubed minus m, so that's going to be 2 cubed minus 2. So 8 minus 2 is 6 over 12. So that's going to be a half. And then we've got this element C. So in the end here, we'll have 4L sub 0 plus this element C. Okay, so those are some examples of calculations in the Lie algebra. And now what we want to do is form a polynomial algebra whose variables come from this Lie algebra, where the commutativity is given by this structure right here. So let's maybe go ahead and clean this up and we'll look at that. So on the last board, we looked at the notion of the Verasoro Li Algebra, and we pointed out that maybe if we could form a polynomial algebra out of this Verasoro Li Algebra, that would be something interesting to look at. And that's exactly what we're going to do here. So I'm going to call this U of V. So this is essentially something like the universal enveloping algebra. Maybe we'll construct that carefully later. But what it is, or how we want to think about it, is as a polynomial algebra with variables L sub minus m. So in other words, the variables are elements from the Lie algebra. And the commutativity of the variables goes like this. So L sub m times L sub n minus L sub n times L sub m is the bracket of L sub m and L sub n. So the important thing here is up here, this bracket is not a commutator. It's often called a commutator, but really this is the Lie product, or the Lie bracket. But when we push this structure to a polynomial algebra, now we replace the Lie bracket with this commutator, which is this like AB minus BA type thing. And another important thing that we're doing is we're replacing this C, this central element, with just some number. And we'll actually do this just by calling it the same name. So it'll just be the number C, instead of up here it was like kind of the abstract vector C. So let's maybe do an example calculation here. So if we do L sub minus 2 with L sub minus 3, so notice we can change the order of that using this rule right here. So notice we can change this to L sub minus 3, L sub minus 2, as long as we subtract the correct bracket. And in this case, we need to subtract the bracket L sub minus 3, L sub minus 2. And we get that just from kind of rearranging this equation right here. So let's see what we get here. So we're gonna have L sub minus 3, L sub minus 2 minus, but then by our formula up here, we see that this is gonna be minus 1, L sub minus 5. But then we don't get anything else because negative 3 plus negative 2 is not 0, so that's it. So in the end, we get L sub minus 3, L sub minus 2, plus L sub minus 5, something like that. And you can similarly rewrite any monomial so that it decreases in indices from right to left. And that's actually going to be an important thing to do that maybe we'll look at later. It's called the PBW theorem. So our big goal here was to discuss what type of vector spaces were important to understand so that we could eventually look at examples of vertex algebras. And what it boiled down to was it's nice to understand polynomial rings and infinitely many variables. If those variables commute, that's okay, that's a good starting point. But we really want to think about what if those variables do not commute, and if we get the commutativity of those variables from the structure of some Lie algebra or some other algebra. And I think we've done that. We've looked at a couple of examples, and we'll come back and look at some of this stuff a little bit more carefully in a forthcoming video. And that's a good place to stop.